So far for equilibrium, we've assumed we've got a little particle, and then we've got some forces acting on that. And we've looked at what calculations you would do to determine if that particle was in equilibrium. And so it's in equilibrium if when you draw the vectors nose to tail that they get a closed path so that your resultant force is zero, or you add up all the x components of these different forces and then you add up the y components, and if they're zero, that particle is going to be in equilibrium. Our next step is to solve problems using static equilibrium. In that case, we'll be told that we've got static equilibrium, and then we're going to do some analysis at a point that's got particle equilibrium in order to figure out an unknown force. Okay, so far we've been shown whether or not it's got static equilibrium. For these problems, we're going to be told that it's got static equilibrium, and then we'll use the rules that the force must add up to zero to find an unknown force. So let me just get rid of this. So the idea of a particle is a bit abstract, but basically it's saying you just choose a point, a point that's either a small fitting or a small portion of this mechanical system, and you're going to check whether that point has got static equilibrium. And typically that's a point where the forces converge. So the same if you're looking at your particle, the forces are all acting on that particle. If we're trying to find the particle, we're just looking for the point where all the forces converge. So for example, it's probably easiest to be seen by example. We've got a box that's being lifted by two fellas so they can put it on a truck. So the truck's going to drive in here, and then they're going to put the box down on top of it. And the question wants to know what's the forces in the rope. And so now we need to choose what particle will be the most useful for finding the unknown forces. So the first thing we'd usually do is just have a think about what are the main forces here, what's causing the tension in that rope. What's causing the tension in the rope is the gravity acting on the box, so the weight of the box, which is acting downwards. We're going to draw that to the center of the box. Now, what's stopping the box from falling? Well, it's the two ropes. And let me just quickly show you something. One of the useful things about ropes or cables or chains for us is that if a force acts on a rope, so suppose I apply a force this way, if a force acts on a rope, the rope will always align with the direction of the force. So if I'm pulling this way, the rope is going to align that way. If I pull in a different direction, so say I pull down this way, if I pull down that way, that rope is lining up with the direction of the force, so the line of action of the force. The similar things happen if this rope was fixed at both ends and you put a weight in the middle. So if we put a weight here, then the rope straightens and lines up, and the forces, if I can let this go without it moving, the forces that are holding a weight up will be aligned with the direction of the rope. So there'll be one force acting this way, there'll be another force acting this way. And so we know that the forces in these ropes are acting like so, and there's another force acting this way. Now you'll notice I'm not being very careful about exactly where I put those, but just somewhere in that rope you've got forces acting this way. Now, if we're trying to figure out what the forces in the rope are, what we're looking for is the point at which these forces converge. So you can see that these forces are all converging onto this little hook at the top of the box. So that's the point that we're going to call the particle, and it's the point we're going to use to analyze this problem. So we're going to say if this whole system's in static equilibrium, this point must be in static equilibrium, and so we're going to use that point to figure out an unknown force. In this case, we'd be figuring out these two forces. Okay, a very similar problem. Again, we've got a cable that's holding up some traffic lights in this case, and we've been asked to figure out what's the tension in the cable holding up the traffic lights. So again, we're starting with whatever force is the cause of the tension in those cables. And so again, it's going to be the gravity acting on the traffic lights, and there's going to be gravity acting on both of them. Assuming they're the same, it's going to be the same gravity. Then we're thinking to ourselves, okay, so why is that traffic light not falling down? Well, it's because there's tension pulling this way, and there's also tension pulling this way. And then if it was just this force, then this traffic light would swing down and hit the pole here. And so there must be something pulling this way as well. And similarly from the other side, pulling that way. So this cable's in tension. It's pulling the traffic light on this side this way. It's pulling the traffic light on this side that way. So this time there's not one point that we could choose because these two gravity forces don't converge. Okay, so they're never going to converge on each other. But we can see the convergence point. We could choose this point, or we could choose this point. Those are the points those forces are converging, and then we could use that for the rest of our analysis. Okay, another similar problem. What's the tension in the four chains connected to this box? So yet again, we're looking what's the cause of all the tension in those cables. Well, the primary force causing the tension in those cables is the weight of the box, which is acting downwards. Then we're also going to have, why is it not falling? So the box is not falling. I'll just draw these by hand because we've got tension force, reaction force, and the chains. And again, we can look for where all these forces are going to converge. And so they're all going to converge on that hook. So that hook is what we're going to use as our particle in this analysis. So we choose that point. But what we'd have to do then is we'd have to think about what are the forces in the chains doing to that point. So at the moment where this arrow is showing what the chain is doing to the box, we would need to think about what the forces in the chains are doing to that point, and we'd have to put them the other way around. So in fact, those chains are trying to pull that point down. And then we'd think to ourselves now, so we've got gravity acting downwards on this box. That must be balanced by these two cables pulling upwards on the hook. And so we'd then get all the forces that are acting on this particle, and then we could use particle equilibrium to figure out missing forces. So the forces we don't know, so we don't know the force in the cables. So we then use this particle and the fact that it's in equilibrium to figure those out. Another problem which shows something a little unusual, but we've got a couple of bungees that are holding up weight. So bungees, like cables or chains, they're flexible, so the force is going to be aligned with the bungee. And so we must have a force acting this way. Well, actually, let me take a step back. We should start with the primary force. So what's causing the tension in those bungees is the weight of this weight. So we'll draw that to the center for now until we learn more about centroids. And then we've got a force aligned with that bungee. We've got another force aligned with this bungee. And we've got to find the particle we're going to use. So we're going to look at the line of actions of all these forces. So these will come to here. This one will come to here. So the particle we're going to use is this one. Now we'll still use that even though there's nothing here. So there's a hole in the middle of the weight, but we can still, it's the point at which the forces converge. That's what we're going to consider for our equilibrium. So it's a little unusual. Even though there's no force there, we're imagining a particle in the center here, and it's the point at which all these forces converge, and that's the particle we're going to look at in order to figure out the unknown forces. This problem is a little bit similar. So again, we've been asked to find the reaction force that the wall exerts on the plate. So to find the particle of interest, so the point that we're going to consider for particle equilibrium, we're just going to trace back the line of action of each force. One like so, one like so, one like so, and all these forces align with the particle here. So we just consider a tiny little section of this plate is going to be what we assume to be the particle, and then we're going to look at the equilibrium of that particle to find out unknown forces. This last problem is a little bit trivial, but it's worth a quick look because it's a little bit different from all the others. So in all the others, we could find a unique point where all those forces converged. So all these forces converging, and then we choose a particle as a small section of that plate, or we choose this particle that's in the middle of nowhere, or we choose this hook, because that's the point at which all the forces converge. For this problem here, we've got a guy in a bungee jump, and he stopped bouncing, and he's come to rest. And so again, we can think of, well, what's the primary force here? Let me just move him up a bit. The primary force is again the weight of the wee fella hanging. So it's the weight of this person hanging from the bungee jump. What's the reaction? Well, the reaction is the tension in this rope, which is going to be acting vertically upwards. Now this time, the two forces are collinear, so they act, or they have the same line of action. And so they don't point towards a single point that we can choose as our particle. What we can do instead is we can just choose any point in this situation. And so as my particle, I can choose a small section of that rope there. And then we can consider, well, and so again, we're thinking, let me just draw it in close up. Oops. So we've got the rope, and we're just choosing a little section of that rope as our particle. And then we can say the force downwards on that particle is equal to the weight of the bungee jumper. The force upwards must be equal to that, because we must have particle equilibrium if the whole system is in static equilibrium. And therefore the force upwards must be identical to the force downwards, which is what we would know anyway. Okay, so having figured out how to identify the particle within a system, we'll now look at how we use particle equilibrium to figure out unknown forces.